All right, let's dive right into it. Today, we're completely unpacking spatial information technology. We're looking closely at how modern systems have moved way beyond just static paper cartography to literally predicting the future of our cities and environments. So if you've ever wondered how city planners and architects pull off complex reallocations or how they build those incredibly intelligent geographic databases, well, you're definitely in the right place.
You know, for centuries, geography was really just about documenting what is where. You found a mountain, you put it on a map, right? But as our world got so much more complex, we needed to know, why is it there? And honestly, more importantly, we needed the digital architecture to actually handle the massive data sets required to answer that question on a global scale.
We have moved so far beyond drafting tables and compasses. I mean, early computer applications were pretty much restricted to basic data processing and some simple graphics. But today we are building something profound. Highly complex digital decision support systems. It's a total paradigm shift. Here is our roadmap for today. We'll start with the big spatial questions, define what exactly GIS is, look at the forms of geographical data, see how to build a spatial database, and finally, we'll get into the true power of spatial analysis. All right, part one, the big spatial questions and how we are moving way beyond the traditional map.
So the absolutely crucial point here is that we need to capture data from all sorts of different sources and integrate it using geoprocessing tools to solve actual real-world allocation problems. Think about the high-stakes questions planners deal with every single day. What's going to happen if a facility is shifted to a new location? Who legitimately benefits from that reallocation? And, who loses out? A basic visual math just can't answer that. We need a true spatial information system to crunch those complex geographic variables and deliver actionable answers.
Moving right along to part two. What exactly is GIS? It's the ultimate amalgamation.
Think of GIS, Geographic Information Systems, as this incredibly powerful amalgamation. It takes computer-assisted cartography and essentially merges it with a heavy-duty database management system. But it absolutely doesn't stop there. To make this massive framework actually function, GIS pulls its conceptual and methodological strength from a wildly diverse set of rigorous disciplines. We're talking computer science, statistics, geography, geology, and hydrology. By synthesizing all of these sciences, GIS lets us organize spatial data, run incredibly deep computations, and actually support critical logistical decisions. It really is the whole shebang.
Which brings us to part three. Forms of geographical data. This is really the DNA of the system.
Think about a standard stock register for a cycle shop. You've got part numbers, quantities, descriptions, wheel spokes, ball bearings, that kind of thing. Now, this data is strictly non-spatial because, well, those parts can just sit in a warehouse anywhere, right? There is no fixed geographic coordinate naturally attached to a wheel rim in a database. Spatial data, on the other hand, absolutely requires an attribute that anchors it to a definitive, real-world map coordinate on Earth, like the exact boundary of an agricultural holding or the specific footprint of a municipal building.
Now, once we actually have that spatial data, it usually takes one of two formats inside the computer: raster or vector. To wrap your head around this, imagine raster data as literally shading in squares on a piece of graph paper. If you try to draw a diagonal line, a raster file represents it by dividing that paper into a matrix of tiny little rectangles or cells and assigns a value to each one based on its row and column. Vector data, however, represents the object as a set of precise lines and polygons drawn between specific coordinate points. It's kind of like playing a highly precise game of connect the dots. Both have their specific uses, but they represent two fundamentally different ways the machine mathematically sees our world.
All right, on to part four, building the spatial database. Basically, our digital assembly line.
So the GIS assembly line kicks off with manual data input. Digitizers and scanners are used to literally bridge the gap between physical, old-school paper maps and our digital core, which obviously saves an immense amount of time compared to manually keying in thousands of coordinates. Next up, spatial errors in those cell values have to be meticulously corrected. And finally, we do data conversion. We are usually transforming that vector data over into raster data, basically because the bulk of really complex spatial analysis just operates best and fastest in a uniform raster domain.
And finally, part five, the power of spatial analysis. This is where we solve the real problems. This is the ultimate payoff.
What truly distinguishes GIS from just a standard, run-of-the-mill database are these specific spatial analysis functions. These operations use the spatial and non-spatial attributes we've been tracking to answer real, pressing questions. They transform raw data into highly actionable intel. Now, while there are a bunch of different operations, like network analysis or digital terrain models, the true heavy lifters, we really need to focus on are overlay analysis and buffer analysis.
Okay, so the absolute hallmark of GIS is overlay operations. Imagine taking a stack of transparent maps and laying them directly over one another on a light table. If you want to determine the most productive soil for a very specific crop, you can't just look at a soil map. You need to take a map of soil types and literally overlay it with a map showing crop productivity for that exact same geographical area. By mathematically calculating the combinations of soil and productivity across these integrated layers, GIS instantly pinpoints the most fertile farming zones and generates a completely new map layer to guide agricultural decisions. It is incredibly powerful.
And then we have buffer analysis, which is just phenomenal for studying proximity and accessibility. Let's say you're mapping out major hospitals in cities like Muzaffarnagar, Meerut, Ghaziabad, and Aligarh. GIS can create buffers, essentially these geographic catchment zones around all of these facilities. This specific analysis instantly and visually reveals that populations closer to the urban centers are well served, but at the exact same time, it highlights exactly which distant populations are vulnerable and have to travel unacceptably long distances just to utilize life-saving medical services. For public health planning, this is an absolute game changer.
And that really brings us full circle. I'm going to leave you with this thought to chew on. Consider how GIS could be used in your own city right now. If your local government decides to shift a public facility, like a school, a fire station, or a transit hub, to a totally new location, who actually benefits from that? And honestly, more importantly, who is expected to lose their access? Thanks to spatial information technology, we don't have to guess anymore. We literally have the digital decision support systems to know for sure. Keep that in mind the next time you look at a map.